I'm going to introduce the next session, which is all around accelerators. This is actually has lots of connections with the other efforts which we kind of talked about in the beginning of the workshop. It connects in with the application-defined networking. It also connects in with energy efficiency. So there's a broad set of collaborations across these different thrusts. So the other fantastic thing was I managed to get a bunch of people to do all the motivation for this earlier in the day. Dave Patterson's talk, as well as Dave Moll's talk, as well as Stephanie's talk, just really leads into the various different material that's going to happen in this session. So, so the first one is clearly there's increasing specialization. There's specialized hardware for a really wide range of use cases. They end up improving performance, they end up reducing costs, they increase energy efficiency, and so on and so forth. And just to make this very concrete as to what I mean by accelerators, here's some canonical examples that I've kind of listed. So, you have ML accelerators, such as TPUs and GPUs. You have domain-specific accelerators, such as, say, video transcoding. And then you also have various other kinds of accelerators, such as compute, which is coupled with SSDs, for instance. So you have computational SSDs. And you also have accelerators which are coupled with networking and storage, which are essentially used for accelerating remote access. So these are compression, encryption engines, things which you find on SmartNICs, network accelerators, and a whole bunch of other devices. So in some sense, accelerators come in two packages, big accelerators and small accelerators. And the big accelerators, you can think of them as standalone entities which, with substantial amount of computing and need to network explicitly. So networking is essentially becomes a slave in some sense for these big accelerators. And then for the small accelerators, what we have is that the roles are a bit reversed. These are traversed in line, and where networking, it's coupled with networking, and in some sense often used to make networking go faster or remote access go faster, and it's often used for cloud infrastructure purposes, such as networking and storage access. So what we're doing at UW is to cover both of these types of accelerators, trying to enable programmability for both types, both the big and the small, and I'm going to describe the various things which are happening in that space. The other trend is clearly there's a lot of promise for disaggregation and consolidation. It's still not been delivered in many ways, but there are certain areas where it's actually seeming to play out. And the promise really is that you can actually substantially reduce the amount of resource stranding if you can have pools of resources and can allocate them independently and have them be networked enough so that you can actually put together whatever kind of configuration you want to support the application that you want to run. And so again, there's actually an interesting sort of contrast. That is, you might need disaggregation for accelerators, where you can enable independent scaling of different accelerator tiers. And this goes back to the big accelerator kind of description that I had in the previous slide. That is, in those cases, you're really kind of putting together this jigsaw puzzle of different types, and they are networked together using disaggregation. And there's the other aspect of it, which is that disaggregation itself becomes easier if you actually use the small accelerators so that you can sort of get the efficiency benefits for remote access, for remote storage, and remote networking. And then, the other piece, which is really kind of elevating networking as a first-order entity in the context of accelerators, is that it's often co-designed. These accelerators, especially the small ones, are really co-designed with networking. That is, you end up co-locating a whole bunch of. Since I'm producing a SmartNIC, I get to make up exactly the set of things that I want to go with the SmartNIC, with the networking and storage access requirements of the SmartNIC. So you end up having a makeup of computing elements which is very unique and tailor-made for remote access purposes. That's on one side. And the other side is that SmartNICs themselves end up being these very nice, lightweight entities which can host a device tray in some sense of, say, SSDs or TPUs or GPUs and things of that sort. So that becomes a low-cost and an energy-efficient way of deployment of devices in your data center. So So the outlook for data centers is that if these things are indeed successful and if disaggregation were to actually take hold, that you will have distributed systems of heterogeneous hardware accelerators. And multiple types of accelerators might be used for accelerating a specific application. They will communicate and span across different types of networks. I didn't really mention CXL, but put in whatever sort of descriptions of CXL here as well. And they have to support multi-tenant workloads. So that's kind of the requirements that we're going to work with. So the premise for a lot of the talks which are going to happen in this session is that how do you build systems which can effectively manage, compose, and utilize these accelerator tiers? And there are really two parts to this question, and this really ties back to this question of there being big accelerators and small accelerators, which is that how do you enable the deployment of clouds of accelerators, in which case these are clouds of big accelerators. And the second part of the question really is how do you achieve an efficient disaggregated infrastructure, that is how do you accelerate the cloud using all of the small little accelerators that you find on various devices. So I'm going to briefly describe these two thrusts. And then the first direction, which is the cloud of accelerator stack, is really what most of the talks in this session is going to focus on. And it's really trying to figure out what is the networking and distributed systems kind of layers or mechanisms or tools that you need in order to enable this vision of cloud of accelerators. So the first one is really that since these are going to be standalone entities which are going to be networked, networking needs to be implemented on these accelerators in the most modular fashion, the most extensible fashion, and the most efficient fashion possible. This also ties back to Dave's vision that you're going to have these devices which are going to be directly plugged into the network. And Katie is going to describe her work on putting a networking stack on accelerators. Moving up the stack, if the connection which is coming out of these accelerators is actually an optical interconnect, then you have tremendous flexibility in how you do topology engineering. So we've been working on ways in which we can have an algorithmic framework for distilling topologies which are tailor-made for the collective communications or any kind of communication workload that you might actually want to target. And Liangyu is actually going to talk about that. And then further up the stack, if you have these collections of accelerators, how do you schedule a particular tenant's workload, which might actually invoke various different kinds of operations? How do you batch them together? How do you increase the efficiency of these accelerators while meeting SLOs? And that's the topic that Lequn is going to describe. And then there's even further up, we are going to try to gang schedule these accelerators across multiple tenants. And Tapan has done some extremely interesting work. He's not going to talk about it, but he has a poster that you can go and you can go and find out more about it. So that's one direction. The second direction is this, and I'm just going to say this just so that I can introduce you to the students that you can then go and talk to later. But we're not going to have any talks about this in this FOCI session. Maybe it'll happen in the next one, which is that going back to this small accelerators and accelerating the cloud infrastructure using the small accelerators, we are building out a framework for programmable disaggregated storage and being able to place distributed computations all the way from the storage device all the way to the entity which is going to consume them. An example application for this is ML ingestion. There's this very interesting paper from Meta which kind of really describes what are all the transformations that have to be made in order to take the data from storage before it's actually consumed by the ML computation. And that's an example, target example that we are targeting. This also lets us enable much higher level abstractions, such as elastic SSDs, which are really spread across multiple physical SSDs, which grow and shrink based on what the requirements are for the tenants. And also provides, we also want to provide efficiency, fairness properties, and all those different kind of things. How am I doing on time? Okay, so let me wrap it up very fast. So this is our model. This is another way where we have a tie-in with application-defined networking space, which is, let's say you have a specification of what the application wants to do when it wants to access the data and wants to perform various sets of operations on it. So let's say that's specified in a domain-specific language way, just like what we have in ADN. How do you actually put that across a whole bunch of devices, SmartNIC on the server, SmartNIC on the device tray, which is actually hosting the device tray, programmable switches and network accelerator cards, and so on and so forth. So we've done a bunch of work in this space. Jae Hong, who is over there, has been working on SmartNIC-based JBOF devices. He's been able to build a system where SmartNIC is hosting some number of SSDs, provides congestion control and quality of service at the target side, and provides maximum utilization of the SSDs in the first place. And then Frank, over there, has been working on container offloads. He's been looking at offloading the networking stack and optimizing it using acceleration. And Rajat, over there, is been looking at the ML ingestion as an example case study, and how do you spray these computations across these different devices. So having said all that, I'm just going to simply just conclude. Distributed accelerators are going to be an integral part of cloud computing. You would need distributed and network systems to make effective use of these accelerator tiers. At the same time, you can also take advantage of these acceleration capabilities, which come in small accelerators, to make DISAC practical and efficient. And that's the vision that we're kind of working towards. So happy to take questions, or maybe I should just pass it along to the next speaker, who is Katie. Katie is a student who is working with Tom, and she's going to be describing the work that she's been doing on putting a network stack on accelerators.
Is this okay?
I think it should be okay.
Okay, great. Awesome. Yeah, so today I'm going to talk about Beehive, which is our work on building a modular, flexible network stack for direct attached accelerators. I do this work with a couple other students here, Matthew at piano, the postdoc, Pratush, and then some people at MSR as well. So we've heard a lot about accelerators in the data center. This is just more motivation for that. But one thing that I do want to kind of look at is there are kind of two different categories. There's some application stuff. So these are things like, you know, video encoding at Facebook or ML at Google, Facebook, or Microsoft, as well as kind of the infrastructure, which was kind of mentioned a bit in the talk about like Amazon's infrastructure. So they do network virtualization. Amazon also does storage and a bunch of other kind of virtualization offload of like infrastructure things into accelerators. And so this is a look more specifically at kind of application accelerators. And basically we see that, you know, various research has shown that you can have accelerators have energy efficiency benefits across a wide range of applications. But specifically, a lot of these numbers was looking at basically like if you go and read an ASPLIS paper or a micro paper, what do the results show? And so they're kind of evaluated kind of just in, you know, the simulation or kind of not integrated with an overall system. And so these numbers kind of don't really account for the surrounding infrastructure that you need to integrate these accelerators into a system. So one way that we are interested in looking at is network attached accelerators. So in this case, they're directly attached to the network so they can communicate without CPU interventions. This is the diagram at the very top where basically you have in from the network, it just goes through your Mac to your networking hardware and then to an accelerator, maybe to some DRAM either off chip or on the board. But here you never ever touch the host CPU, for example. And so Microsoft and IBM have both published some papers about deployments of FPGAs that they attach to their general purpose data center network. And so this means that you can get energy efficiency benefits both for the applications you're offloading as well as for the infrastructure like the networking and such. So we're really interested in what should a hardware network stack look like for this case. Basically, what features do we need to provide, and what do we want to prioritize in terms of design goals to enable us to better integrate accelerators into our network. So the first thing we started with was looking at software network stacks. So I've just lost my speaker now. All right, whatever. Basically, we were looking at Google Snap and eBPF and kind of what their aims are at the moment. And we see a lot of them really prioritizing modularity and customizability and kind of being able to experiment with different implementations of things. So we see some work at the protocol level. So in particular, Snap, which is Google Stack, integrates a new transport protocol. And there's a lot of different transport protocols that have been flying around alongside TCP as proposed alternatives. So we want to be able to kind of support experimentation with that. And then we also see custom network functions. So if you look up a lot of the eBPF work right now, you'll see a lot of work on custom load balancers. So like Cloudflare has one, Facebook has one, and this sort of stuff, as well as kind of network virtualization. So there's like all these things that coexist together. And they're interconnected in complex ways in the stack. So you might have a packet that goes from Ethernet to IP, but then has some sort of virtualization layer. And these kind of virtualization encapsulations can differ, but maybe then they all need to go through the L4 load balancer before going on to their transport protocol and something like that. And then potentially all layers are going to need control plane access. So the ability for the control plane to reach down and kind of manipulate the parameters that they're using underneath. So our proposal for this is called Beehive, which is a scalable network-on-chip based network stack, which is a lot of uses the word network. Basically, our intent is that each protocol or network function becomes a tile, and then the tiles communicate through message passing, and you can compose them basically. So in this particular diagram, we've kind of broken it down by protocol. There's various granularities that you could do this at. So if you know that, say, Ethernet and IP often coexist together, you can combine them into a tile. But one of the nice things about breaking them up is that it becomes really easy to interpose things, say, between two protocol layers. The other nice thing that comes with using kind of a scalable NOC-based stack is that then you can scale up processing capacity by duplicating tiles within the architecture. So if I wanted more processing bandwidth for my TCP stack, say because the one that I've implemented only runs at 10 gigabits per second, but like the full traffic I'm going to receive is more going to be like 40, then you could have 4 instances of those. You then have to deal with some of the routing stuff, but it at least provides you the ability to have the capacity. And so we're really focusing here on providing support for both flexible packet operations, which are the kind of things that are often supported previously with things like P4 really well, but we also want to be able to support reliable protocols and things that are stateful. So we're going to look a little bit at how we process a packet. So basically, it's kind of like a pipeline of layers. So in the first step, you would get in the full payload. In the Ethernet kind of processing layer, you strip off the Ethernet header. You do whatever you need to, drop the packet if it's not for you, or deal with any virtualization. And then you would pass on kind of the metadata parsed out, and then in the payload, kind of the rest of the unparsed packet to the IP layer, which does much the same thing. In this case, this is a UDP stack, so then at the end, right, you would go to the application. But we've done this with instead of UDP, you have TCP, and then also some other stuff in here, which there's a more complex one that I'll describe for the benchmarking stuff. This is just the transmit path, which is much the same, except instead of stripping off, you kind of build up step by step. So for our prototype, we went and prototyped this on an Alveo U200 running at 250 megahertz. And we're using a 512-bit NOC, so this just means that you can get 100 gigabits of traffic through your NOC. The protocols that we have were Ethernet, IP, TCP, and UDP, and then we had some network functions, either NAT or IP encapsulation. We have a test bed. It's not super important. Everything was connected to the same switch, I guess, if you want numbers for that. So I'm going to look at one experiment here. We have some other experiments, but this is one we did because I think it showcases both the TCP stuff and also some of the network virtualization stuff. But our intent here is to migrate an established TCP connection between two CPU clients. And here we're using the demi-kernel TCP stack because specifically they have a way to basically pull out all this TCP state for a connection and transfer it to another machine and start processing from there, at least on their side. But it does require some modification on our side. So on our side, we installed basically like a little IP, it was a NAT, little NAT rewriting module basically into the FPGA server that basically keeps kind of, hey, if I see, right, like a packet from a different tuple, right, what is it actually going to be for my TCP engine? So in this case, we start on CPU client 1, right, with a particular physical IP, and it's just sending a bunch of echoes back and forth. And then we go and migrate the TCP state to the second client, which is going to have a different physical IP. And so then we tell the FPGA server, hey, you know, when you see this flow tuple, right, and you, if you're using this in your internal kind of stack, instead of trying to send it to 198.0.0.1, which was the old client, please instead send it to 198.0.0.11. And so then, you know, after that, we can just start sending again an echo to the second client. So we went and took like a little throughput over time graph, and you can see the requests are coming from the first CPU client, and then migration occurs, and that takes us around 500 microseconds. We didn't super optimize this. In fact, like the serialization of the state was JSON, so that's part of it. And then there's requests coming from the second CPU client, but we can see that the throughput kind of recovers and goes back to normal. And so then now I'm going to move on to talking about kind of the ongoing and future work that we have. So kind of the next stuff that we're very currently working on is internal load balancing kind of across duplicated components to support multiple instances of tiles to allow scaling of processing capacity. And then kind of future work that we haven't yet started would be integrating with the CPU to offload some of the application-defined networking policy enforcement, which we heard about earlier. So for our scale-out workload, we decided to try and try and do some acceleration for view-stamped replication. So we know that consensus algorithms are really important for getting strongly consistent operations, even in the face of node failures. But for consensus to work, right, the leader has to contact a majority of nodes. So like this diagram on the right, which probably many people have seen in their distributed systems class, which is very common. But basically, there's this like little phase in the purple box where the leader will go and contact, you know, a majority of nodes. And as an optimization, right, you can have certain nodes that do not need to run the full application. They just need to know who the leader is and where the what operations have been agreed upon and what view we're in and things like that. So you can have some cheaper nodes that don't maintain the full state and don't do application logic. And so in this kind of system, when you're running an application, say that's doing reads or writes, it's very common to do stale reads at the application level because the process of going to agree on who the leader is and making sure everything is up to date is pretty expensive. But then the applications have to have logic to deal with this inconsistent data themselves. So for things like, you know, if you're checking your privacy settings, or, you know, bank statements or things like that, you really want to have this strong consistency. So the question we wanted to see here was, can we make, you know, up-to-date reads cheaper by accelerating the witness nodes? We found this particular situation, we thought it would be advantageous for hardware for a couple reasons. The first is that the witness nodes don't need to execute application logic, right? They just need to keep state kind of about the overall configuration of the system. The other thing is messages are typically small packets. So this is nice specifically because the FPGAs tend to be a little bit better at dealing with small packets than CPUs. And our goal here is that we want to provide relatively cheap compared to maybe running this on a CPU, but also high throughput witness nodes with low latency replies to any operations. And here we specifically want to leverage Beehive's scale-out capabilities so we could host witnesses for multiple shards in one FPGA. So the typical way for scaling up kind of bandwidth in these consensus systems is to maintain multiple shards of your data. And so it seemed really kind of natural to kind of reuse Beehive stuff to allow us to host multiple shards. So this way we can use up kind of the excess processing capacity that it has without you know, instantiating a whole nother FPGA design or something like that. So We have some preliminary results. This is the estimated performance from simulation of just the accelerator alone. But if you look at kind of like, oh, if we can feed, operations into this accelerator as fast as possible, what can we do? And that's about 64 nanoseconds per consensus round is our latency, not including the network stack. So this is just the engine itself. If you could just feed packets directly into it. And the bandwidth would give you about 15.6 mega rounds per second, which turns out to be about 2 gigabits per second of actual data throughput, which is not particularly large, which does suggest that, if you wanted to go and replicate to multiple shards and have multiple things of these, you could have quite a few without kind of, in order to saturate the whole 100 gigabits per second, so you could have quite a few witnesses on there. So we went and implemented this. I ran it through implementation. Just to make sure that it's a feasible design. The utilization is fairly small. This little pink block at the bottom. And so we think it's promising that we can replicate this tile to scale up processing bandwidth. The implementation kind of critical path where kind of things that makes it kind of unfeasible is that you have to buffer some data, and kind of as that buffer gets larger, it gets harder to get this design to meet timing. And then a slide on just the future where we want to move forward to integrate with PCIe to allow our interaction with CPU applications to offload this application level networking. So as we heard earlier, service meshes are applying policy at the RPC level. And so basically we're asking, can we interpose on traffic to offload RPC level policy to hardware? So for example, what does the interaction with the CPU infrastructure look like? How are we going to go and get all those rules? And also, is there kind of a generic processing model? I think Zhangfeng alluded to this kind of like, in the P4 model, but maybe for L7. So is there a generic processing model that we could define in order to provide like a kind of a hardware programmable L7 policy engine? I think that's all my slides.
I like that Beehive layout. It does make you think as a way of building programmable data planes. Like, how do you contrast with the other approach, the PSI approach versus this one? Suppose that was my goal. I know your goals are broader, but I'm just kind of wanted to just focus on that. Suppose you wanted a programmable data plane. Like, how would you contrast your approach to that one?
So I guess there's a couple things there. For one kind of portion is the processing element part of it. So in the PISA model, of my understanding is, all the elements are relatively similar, right? This kind of match action kind of thing. And I guess there's some differences there in that's kind of restrictive. Our processing elements are kind of, we will let them be anything. Kind of they just, there's going to have to be like a higher level contract between the processing elements. Kind of like, if I'm receiving something from the IP layer, like it's always going to have a certain format. And so it has to agree on that rather than kind of just a uniform processing model. The other thing would be the interconnection. So I guess this kind of depends, is that like a lot of the PISA implementations that I know about at the moment are more pipeline-y. Whereas this is a little bit more flexible. There's a little bit more room to maneuver around. And there's a lot of research into network on chip in general. And so moving kind of more towards that model lets you kind of leverage that instead. So one particular direction that like I think might be interesting is, for when we talk about virtualization and isolation and stuff, there's a lot of work into NOC virtualization. And so there's like a question there I think is like, can we leverage some of that in order to give us kind of the virtualization and isolation we need by very specifically kind of moving that way and choosing to use that.
Just quick follow-on, so given that flexibility of processing, is there a way to reason about being line rate?
About being line rate?
Yeah.
So it depends. I mean, so, obviously some of it depends on the bandwidth of your modules and like what you are allowed to drop and when. So, if you're doing all kind of unreliable traffic and you're allowed to drop everything, it's like if anybody ever back pressures me, I'll just drop the packet. And that will give you line rate, but maybe it's not the line rate you want, and it's not the line rate your application is going to want. Obviously, as you move up to kind of reliable traffic, there's a question of like, okay, what do I drop in when? And that's kind of more of like a policy question that I don't know quite the answer to, and I think it depends kind of like what the things inside your system actually want. And so, hopefully we would be able to provide the infrastructure that people could build kind of the policy that they want inside it.
Thank you.
Is there any overlap or synergy with the talk we've just heard on offloading stuff to the smart NIC? Should, instead of being integrated with the CPU, you just put in the smart NIC? Apparently, we can do a lot in that.
Oh, like so if you wanted, yeah, so you could, this particular work in particular was kind of targeted at if you want to take a big accelerator, kind of in the way that Arvind characterized them and attach them to networks. So like a very, not necessarily like a little offload, but kind of like more like a key value store, more of an application. And you could definitely, there's definitely like, work on offloading that to the SmartNIC and stuff like that and things that have happened there. Some of this kind of, when we go and offload the L7 policy, for example, right? Like there's some of that could also be done on a SmartNIC. I assume here we're talking about like CPU SmartNICs. And so there's a trade-off of like whether you want to do it kind of on a CPU core or in hardware. And, that's a question that I think, you could ask. I think probably our take for this in particular was like if we're moving towards really high bandwidth, we're going to want to pull stuff off of CPUs kind of as much as possible. And so my kind of take on that is just like, okay, let's see how much stuff we can pull off CPUs and how crazy it gets, I guess.
Maybe one other thing is the context is direct attached beefy accelerator.
Yeah.
Which means that I might as well put a network kind of element on it. And there's no, there's, in some sense, it's not an FPGA SmartNIC which is living across from a CPU. Here the master is the accelerator itself and the application logic is
Yeah, I guess I will say that there's like a previous paper where they hosted GPUs on an ARM-based SmartNIC, and kind of the performance was either the same or a little bit worse as hosting it kind of on normal host cores. And so, if you just want to trade off between CPUs, that's great, but it's like if you want to go faster, right, if you want to make sure you can feed this accelerator from the network kind of with the bandwidth that you want, and you want it to go even faster, right, you might have to go down to hardware at that point.
I mean, if the big difference is really the size of the processor in the NIC, if I push to the limit, and you have these very powerful accelerators dedicated for network, should the NIC be on it? Instead of, like just make the network come through it, then you have the right point to modify everything before giving to the main processor.
As in, like, should the NIC be on the same die as the accelerator, or
in the same card, right? Instead,
yeah.
why passing the PCIe?
Yeah, no, I think that's reasonable. And in this particular thing, we're all FPGA. And so, our endpoint is always FPGA. I would say that one of the things I had in mind moving forward, right, is that, what if you wanted to do kind of a combined architecture where some of these little tile blocks are going to be ASICs rather than FPGA. And in that sense, kind of the interconnection becomes even more important because those pins that come out of the ASIC are going to be fixed. And so it's really necessary that we kind of have a good kind of messaging setup that would let you do something like harden certain blocks. And leave others to be flexible.
Thanks.
Thanks very much. An algorithmic framework for taking advantage of optical network reconfiguration capabilities in the context of ML.
Hi everyone, I'm Liangyu. I'll talk about efficient direct connect topologies for collective communication. And this work is a collaboration between University of Washington, recent BBN, and also MIT. So what is collective communication? Collective communication refers to communication patterns in which a group of nodes in a parallel computing system exchange information. So common types of collective communication include broadcast, reduce, all reduce, and all to all, etc. So this was originally a topic in high-performance computing, like in the supercomputers. But it is now extensively used for parameter synchronization in distributed ML training and inferencing. And it has actually become a significant overhead. And how do we deal this overhead? We have already heard a lot about optical today. So yeah, the solution is to use optical circuit network to achieve higher bandwidths at reasonable capital expenditure and energy cost. So optical network is fundamentally different from like the traditional data center network. In optical network, a node is directly connected to another node via optical circuit instead of through electrical switch. An unconnected pair of nodes actually cannot communicate directly. And another point, another difference about optical circuit is that optical circuit actually has high reconfiguration or rewiring latency. So it requires a relatively fixed topology, especially for collective communication. And in this area, we currently have like research prototypes, CPML from CCOM, and also TopOp from NSDI. And most recently, we also have TPU V4 from Google, also using optical circuit network to accelerate ML workload. So because optical circuit requires this relatively fixed topology, so a problem is raised that given the hardware and the workload specifications, how do we find the topology and the corresponding communication schedule to achieve the best collective communication performance? So the hardware specifications include things like the degree of the topology, which is usually like the number of ports on the network hardware, and also like what is the bandwidth of the links, and also the latency of send receive. From the workload side, we need to know like how many nodes do we need for this workload, and what's the size of the data we need to reduce. So in ML, especially data parallel ML training, the size of the data is usually the model size. So we have some observations. The first observation is that coming up with a topology and communication schedule is very hard at large scale. So if we want to come up with hundreds number of nodes topology, it is very hard to design it in an efficient way. And if we want to use computer to direct search for either topology or schedule, then this can easily be an intractable optimization problem, at least for classical computers. So the question is, can we design efficient topology and schedule at small scale first, and then expand them to large scale? So based on this motivation, we have developed several expansion techniques. So given like base topology and communication schedule at very small scale, we have like graph transformations to expand the base topology into larger ones. And the base schedule is also expanded to match the expanded topology. And we have shown that the sacrifice in the schedule performance is mathematically bounded in this expansion process. So here we have shown two examples of the expansion techniques, the line graph expansion and degree expansion. So the line graph expansion expands the number of nodes while maintaining the same degree of the topology, which is actually very beneficial because the degree is constrained by the hardware limits. And the degree expansion, on the other hand, expands the number of nodes and the degree at the same time. So given these expansion techniques, we again have some observations. We observed that different expansion techniques expand the number of nodes and the degree of the topology differently, and they actually offer different performance trade-off. For example, the line graph expansion is very good at latency performance, which is important when your data size is very small. And on the other hand, the degree expansion is very good in terms of bandwidth performance. So it is very beneficial when you have very large data size. And on the other hand, we also have various base topology and schedules to apply these expansion techniques. So the question is, given the target hardware and workload, how can we construct the best topology and schedules using these expansion techniques? So we have developed a topology finder. What the topology finder does is, given a target topology size, the topology finder will explore the possible base topologies and apply combinations of expansion techniques to reach the target size. So for example, the table on the right here shows the result for 1024 number of node topology at degree 4. So we have a bunch of results here. The top topology is a generalized cost graph without any expansion. And the second one is the expansion, line graph expansion of circulant graph. And the last topology is the Cartesian product of different sized rings. So we have a bunch of topologies generated by the topology finder. And actually, these resulting candidates form a Pareto frontier, which means that no one topology is better than another in both latency performance and bandwidth performance. So given this Pareto frontier, we will look at the hardware workload specifications, and based on the hardware, based on what's the bandwidth, latency, and the data size, we can compute the expected or reduced time of all these topologies, and we can choose the lowest one for deployment. So again, we have some observations. The expansion techniques actually have huge gaps in the coverage of topology sizes. So for example, given a topology with size 4 and degree 2, the expansion techniques can only generate topologies of size 8, 16, 32 number of nodes. So there's actually huge gaps in between these numbers that we cannot generate, we cannot construct a schedule. And there actually exists off-the-shelf topologies from graph theory with favorable characteristics. So for example, the low diameter of expander graphs in graph theory, the low diameter is very beneficial for latency performance, which is very important when data size is small. So given a topology, can we efficiently construct an efficient schedule for it? So there are two efficient here. The second efficient is straightforward. We need a efficient schedule to perform the collective computation in high performance. But the first efficient is actually very important. How can we efficiently construct the schedule? So there are some existing solutions in this area. So earlier work has already explored ways to generate a communication schedule for a given topology. So SQL from people uses SMT solver to generate schedule, and Taco from NSDI use mixed integer linear program to generate schedule. Both approaches have a problem that they have poor scalability because they both involve NP-hard optimization. So to see some numbers, we have tried SQL and Taco on Hypercube and 2D torus. And as you can see, that when the topology size reaches like 30 or 60 number of nodes, SQL takes more than 10,000 seconds to generate schedule, and Taco just gave up because of internal timeout. So to deal with this scalability problem, we have proposed what we call breadth-first broadcast schedule. So what we did is we enforce a breadth-first broadcast order for the all-gather schedule generation. So the all-gather is just essentially every node is broadcasting amount of data to every other node. And by doing this, we actually aim to find the best schedule among all BFB schedules instead of all the space of possible schedules. The advantage of doing this is that the scheduling problem can be formulated as a linear program now, which can be efficiently solved in polynomial time. But there's also a disadvantage. The BFB's generation actually does not guarantee we have an optimal schedule for any arbitrary topology. But we have mathematically proved that it actually provides optimal schedules for many topologies with inherent symmetry. So for example, like topologies like torus, Hypercube, and remarkably, the twisted torus used by TPU v4. For these topologies, we actually can prove that we generate optimal schedules for them. So to compare BFB versus the existing solutions, so while SQL and Taco takes like thousands of seconds or tens of thousands of seconds to generate schedule for nodes at tens of number of nodes, so we can achieve, we can generate schedule less than 1 second. And even at the 1,000th node scale, we can still generate a schedule around 1 millionth. So this is orders of magnitude faster than previous work. So we have evaluated our techniques on optical testbed. So the testbed consists of 12 servers, each with an NVIDIA A100 GPU. And the topology is reconfigurable via an optical patch panel, shown on the right figure here. Well, the first evaluation we done is we we do a all-reduced evaluation. So we have used our topology finder to generate the best topology from size 5 all the way up to size 12. And we compare the all-reduced performance of our topologies against shifted rings from TopOpt, and also the classical topology double binary tree. So the result is that our topologies consistently outperform baselines across all topology sizes and all reduced data sizes. So especially for the baselines, the shifted ring, for example, the shifted rings can only perform well at very large data size at 1 GB, but because it has a linear number of hops in the schedule, so it has poor latency performance. So it performs very, very bad when we have like only 1 KB or data size. And on the other hand, double binary tree performs well, very small data size, but it performs like twice. It takes twice the runtime at very large size. And we also have done a data parallel DNN training evaluation on our testbed. So we have done a small-scale 8-node experiment, training experiment on our testbed. And at the same time, we perform a large-scale 1024-node simulated training. We do these experiments on numerous neural network models. And we have seen that at the 8-node scale, we have 30% improvement in terms of total reduced time, which is the total amount of time we spent, the algorithm spent in terms of communication. At the mini-batch time, we see 10% improvement. It is like the end-to-end time cost of a forward pass backward pass. And we have seen orders of magnitude improvements at large scale. So at 1024 number of nodes, we see 6.7 times improvement in terms of total reduced time over the closest baseline, and also 2.6 improvement in terms of mini-batch time. And because collective communication is closely related to high-performance computing, we have also done an evaluation using Frontera supercomputer at the Texas Advanced Computing Center. So we use up to 54 nodes in a 4D torus to do our evaluation. And because the topology of the supercomputer is fixed, it's not reconfigurable. So we tested our schedule generation on this supercomputer. So we used our BFB schedule generation to compare against traditional torus scheduling from the HPC, and also compare against the schedule generated by Sequel and Taco. So what we see is that BFB torus schedules achieve top performance in all torus constructions. So the traditional torus scheduling from HPC only performs well when the torus has equal dimensions like the middle one. So for example, like at the left one, the torus actually has unequal dimensions. So while BFB can achieve high performance, but the traditional torus scheduling significantly underperform BFB. And as for Sequel and Taco, they can only generate a schedule in smaller torus. And actually, Taco also have a performance issue in this setting. So to summarize, we have the contributions we have is firstly there are expansion techniques for synthesizing large-scale collective communication topologies and schedules, and we have a polynomial time schedule generation for large-scale network topologies. And we developed a topology finder to generate Pareto efficient topology and schedules for target hardware and workload. And finally, to run our schedules on CPU and also GPU hardware, we have developed a compiler for lowering communication schedules to the corresponding runtime. Yeah, thank you.
Two questions for you. So the first question is, you also assume an alpha beta cost model when you're doing the scheduling, and most of the work in this space assume that cost model. Do you think that's the right cost model to assume, given the experience you've had running this stuff on hardware? And if yes, why? If not, why? And my second question is, this problem of scheduling is basically the same as multicast traffic engineering. Have you compared against multicast traffic engineering solutions? And if yes, what did you find?
Yeah, so these are very good questions. So first, the first question about the alpha beta cost model. I think my experience is that it works well when your system is, when your network architecture is homogeneous. Like for example, like in the TPU v4, every node and every optical link in the network is homogeneous. In that case, we can conveniently to measure the alpha, and also the alpha is the latency and beta is the bandwidth of the links. So it's very convenient to measure these metrics. But my experience is that when the system becomes heterogeneous, this becomes a very hard problem, because so for example, in the many ML network today, we have NV switch and also IB switch network. In that kind of network, it's very hard to measure the heterogeneous alpha and beta in the system. So in that case, I think alpha beta model is not very suitable in such a case. And the second question about the traffic engineering, we have not done such comparison. So we are mostly comparing to previous works on collective communication results. So yeah, we haven't done that comparison.
So just for clarification, so it seems that you assume, especially for the first part, the part where you reconfigure the network topology according to workload, you assume a kind of supercomputing setting where there's a single workload that has full access to the entire network. Firstly, is that correct?
Yeah.
And secondly, if they're we heard earlier that there's kind of an impetus towards sharing the network infrastructure because that's more cost efficient over many workloads. Would your technique still apply in that scenario, or would it be a wash where basically all of the network is utilized at all of the time, so the topology would likely be a fat tree or be some other expander-based topology that gives equal bandwidth to all parts of the network?
Yeah, about this multi-tenancy, so I think our approach stands if you are still there are a bunch of tasks using the whole network. But if we want to partition the network into different parts, and then let different parts using the different parts running different tasks, then that may be a problem for to apply our work in such a scenario. So the common approach today, so for example, what the TPU v4 does is it slices the torus into different smaller sub-torus, and then they run different jobs on different, basically physically different network. So in that case, as long as the sub topology is still a well-defined expander graph or torus, any topology with inherent symmetry, then this work can nicely apply in that scenario.
Great talk. I have a question, probably some clarification. When you discuss about the topology, or the collective communication, do you think the topology discovery is a major bottleneck or something else? Because from our production experience, running the collective communication, identifying the topology might not be the bottleneck. Something else undergoing in the physical network might be the bottleneck. So what's your opinion?
So actually, I'm not very familiar with this topic. So we actually assume we have the total freedom to reconfigure the topology, and we do not need to find the topology in production. Something I don't know if this answered.
What I mean, because when you do the collective communication, you are basically building the logical topology for the GPU to communicate with each other, right?
Yeah.
And our experience is that building this virtual logical topology might not be the bottleneck. Something else under the physical network might be the issue.
Oh, we actually do not building the logical topology. We are building the physical topology. So we have this optical patch panel. So the physical topology is exactly the logical topology we have. So there's no like mismatch between the logical topology and the physical topology.
Or probably I can share a bit more. So think about it this way: when you run the collective communication, you build a logical topology, right? And then you map the logical topology to the physical topology. For example, if you run the RDMA, then you are doing RDMA QP pairing for each of the GPU node, right? And this kind of physical action in the real physical network might consume more time. That's my experience. So I want to hear about your opinion regarding.
Maybe I can answer this. So one is that one way of thinking about it is that there could be optimizations to the physical layer, which can, of course, be useful, and this is on top of it. So if you were to optimize the RDMA Q pair setup, and you'll have a different alpha beta cost model, which is faster, for instance, and you can just take advantage of it. So this is kind of, you can think of it as an orthogonal issue, but maybe the interesting point that you're bringing up is that might actually be more, there might be more gains to be had from there.
That's exactly my question.
Yeah.
So which is a major bottleneck?
Yeah. We should definitely talk about it offline. Thank you. Okay, so the last talk of the session is Lequn. He's going to be talking about the scheduling problem. The setup is you have a single tenant who wants to perform a bunch of ML computations, and how do you schedule them on a whole bunch of accelerators?
Thanks for the introduction. Today I'm going to present our work, Symphony. So this is about optimizing DNN model serving. We serve in a multi-tenancy task, actually, so we allow serving multiple models, actually. And I know everyone is excited about large language models, but this work is more intended for DNN models, CNN models, like those image classification tasks, like ResNet, MobileNet, this kind of models. So the overview of this kind of model serving system looks like this. Let's say this is an image classification task. Then the client sends the image to a front end. This front end will dispatch this request to one of the backend. And the backend runs the DNN model on the GPU and returns the result back to the front end. And then the front end returns the result back to the client. This is the high-level view of the model serving system. The challenges behind this, I think, include these 3 points. The first thing is the latency constraint. So this is a real-time task. Depending on the task, sometimes the latency can be just a few milliseconds, and sometimes it can be slightly longer, a few hundred milliseconds. This is a latency constraint. And within this latency constraint, you also care about the GPU efficiency. So we all know that batching can give you higher utilization on GPU, but as you batch, you increase the latency. So you want to do this batching, this improving GPU efficiency within the latency constraint. And then the third thing is, when we are operating at the cluster level, the workload changes all the time. In the short term, the request fluctuation happens a lot. Sometimes there will be bursts. You need to be able to handle bursts. And in the long term, cluster-wide resource needs to be rebalanced. Sometimes the popularity changes. Sometimes the overall load changes. You want to release GPU if you don't need that much. This is the long-term workload changes. So if we look at the existing systems, like the previous state-of-art Nexus, they all take the approach of distributed scheduling. So in this type of scheduling scheme, all the components within this system do scheduling. So if you look at the scheduler do the model placement work. So you come up with a schedule that's saying which GPU runs which set of models and with what byte sizes. This is what the scheduler do. And the front ends, they have a pool of backends they can choose. And when a request comes in, they will do a round robin over the backends. They will dispatch the request to the backends. This is their dispatch scheduling. And then the backends, you will receive lots of requests from different front ends, and sometimes it cannot saturate all of them. So you need to select a partial of the request queue to run. So you can see all the components, scheduler, front ends, and backends, they all do schedule. This distributed scheduling has some of the problems. So the first problem is that the front ends, because they are doing this round robin individually, they are not coordinating with each other. So they will amplify the request fluctuation. So the backend will actually see a more burstier request rate than the front end sees. The second thing is this epoch-based scheduling is actually a static partition of the backends to models. So this is very bad for short-term overload. So when a burst comes in, you cannot utilize other idle GPUs. So which means that if you're operating at the cluster level, you need to over-provision to handle these bursts. And a lot of time, you need to over-provision by a lot. And then the third thing is, if one backend becomes overloaded, that means other backends, they are running suboptimal batch sizes. So they are actually running with a reduced batching efficiency. And our system, Symphony, we take another approach that is centralized scheduling. So in this scheme, only the scheduler makes the scheduling decision. The front end, when it receives a request, it will always forward that metadata to the scheduler. The scheduler has all the information from the request side, and also it knows all the status of the GPU, so it can make very clever decisions. The scheduler will send a batch plan to the backend, includes when to run this batch, which model to run, and which requests to be included in this batch. The backend, when you receive this schedule, it just follows this schedule. And it will pull input data from the front ends, and it will execute and return the results to the front ends. And with this centralized scheme, we're able to deliver 5x throughput comparing to state-of-the-art system like Clockwork and Nexus. And here we care about good put instead of just throughput. Good put means the throughput within the latency constraint. So we care about this latency constraint. And besides that, we also achieve very fast response to request fluctuation, and also we can consolidate the GPU usage. So let me explain this graph a little bit. This x-axis is time, and in this first figure, this is the request rate of different models. So these colors, different colors represents a different model, and this grayscale color represents unsatisfied request rate for different models. And as you can see, as this request rate changes, our GPUs in use actually responds very fast to the request rate. And our system is able to consolidate the GPU usage so that it can give advice to the cluster management system, telling you that, probably this time you need more GPUs, and more importantly, when the GPU becomes idle for some time, you can release these GPUs back to the cloud provider, so you can save money. And our system is able to deliver all the latency constraint if it's not overloaded. How we achieve that? So the first technology that we have is this coordinated execution. So with coordinated execution, all the backends that are coordinated by the scheduler, then we can reduce the queuing delay. So in the distributed scheduling scheme, because the execution is not coordinated, the maximum queuing time of a request might be half of the execution time. But in our coordinated scheduling, the maximum queuing delay can be implicitly cut to 1/n times the execution time, where n is the number of GPUs. So when you have shorter queuing delay, then you have more time budget for execution, which means that you can achieve higher batch sizes, which means that you can deliver higher throughput. The second thing is the non-work conserving scheduler. The word non-work conserving means that when the system have work to do, it doesn't do it immediately. Instead, it will wait a little bit to accumulate more requests, and then the system will do it in batch. The benefit of this is it can achieve higher batching efficiency. And we validate this non-work conserving scheduler over different combinations of workload. So we test many different types of models. Some of them have very strong batching effects, some are weaker. And we have tested many different number of models, many different numbers of GPUs, and different tightness of latency SO constraints, and different arrival pattern distribution. Across all these experiments, we found that our non-work conserving scheduler can deliver much better output than work conserving scheduler. Another benefit that our non-work conserving scheduler brings is actually the output stability and also the capability to coordinate with the cluster scheduling to do the auto scaling. So if let's first look at the first figure. So if we are thinking about an ideal system, when the request rate increases, the system initially can satisfy all the requests until at a point that it's at the maximum capacity. Then the ideal system should deliver this peak throughput. But if we look at the current systems, some of them cannot. The output would drop for some reason because of their scheduling inefficiency. So if this is the case, then it's very hard to predict what's the load of this system. We want to achieve this flat top behavior. And then the second property is that when you increase the request rate, the cluster-wide GPU utilization should gradually increase until the point that at the peak output, the cluster-wide GPU utilization reaches 100%. But if you look at some other systems, their GPU utilization increases gradually, but before they reach their peak output, they already reach 100% GPU utilization, and still they can deliver more output because at this time their scheduler have to make better decisions, either implicitly or explicitly. But what that means, you are leaving some performance behind. You are actually not making the most efficient schedule at this period. So if we look at the previous work, they don't have this property. So this will bring lots of challenges to auto-scaling, because when you are operating at this request rate range, you don't know whether to release GPU or not. You are losing some efficiency. And also you are running with, you need more money. So we have seen the benefits of centralized scheduling, and this is a centralized design. Of course, we will worry about the scalability, but we have carefully designed our algorithm so that it's very efficient. We use some very advanced data structure, so its single core performance is very good. You can serve 500,000 requests per second on single core. And then we also design our system to be multi-core scalable, and we have minimum inter-thread synchronization, so we can achieve almost linear multi-core scalability. So you can easily handle 15 million requests per second with our scheduler. To sum up, our work Symphony, it can achieve 5x output comparing to previous work, and it can respond very fast to the request rate change, to the workload change, and it can consolidate GPU usage for the long-term resource provision. And it has the capability to handle millions of requests per second, and it can manage tens of thousands of GPUs. So that's all. And before we enter the Q&A, I actually have one more thing that is, we also do LLM, believe it or not. So we have ongoing work that's serving multiple LoRa fine-tuned LLMs in a multi-tenancy environments, and we can deliver 20x output comparing to Hugging Face transformers. And if you are interested in this, please come chat with me in the poster session.
So you have a centralized scheduler, and it's very performant. So what about what's the story about fault tolerance here?
Yeah, so for the fault tolerance here, the thing is we don't have gray area. Either the scheduler is up or it's down. We don't have a gray area. So you can employ the standard failure detection mechanism to detect this failure. And another thing is our algorithm is deterministic, so you can use replication to do this live migration.
It's work in progress.